castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
So, hi everyone, my name is Matúš Baran, I'm from Slovak University of Technology in Bratislava, and in this presentation I would like to introduce my paper on self-supervised learning of spatial object positioning in football, which I made under the supervision of Igor János. Nowadays, we experience a high demand for intelligent solutions and the use of artificial intelligence, and it is no different in football. Computer vision methods and neural networks have also reached the domain of football, whether it is analyzing the performances of individuals or the entire teams, collecting and evaluating statistics, or even assisting in the form of a video referee. The action spotting, ball action spotting, or the replay grounding, which are challenges from SoccerNet, can serve as an example. Having a common football-specific feature extractor that could be reused in all these challenges could be highly beneficial for both the performance achieved and the time saved. Compared to other domains, however, there are not so many annotated datasets in the football domain. And even the existing ones mostly do not provide sufficient size for quality training. The solution could be in self-supervised learning, where we don't need annotated data, but the existing solutions are mainly focused on the domains that have little to do with football. For this reason, training neural networks in the football domain is challenging. We decided to solve the problem of insufficient datasets using self-supervised learning, and our solution consists in creating a feature extractor specifically for the football domain. We created a new pretext task for self-supervised learning on unannotated data, and we created a large-scale football dataset containing images mostly from the professional football matches. We compared our method with the existing self-supervised learning method, and we evaluated the results on a downstream football task. We created an unlabeled dataset containing over 12 million images, mostly from the professional football matches. In the lower part of the slide, we can see some images from the dataset, and we can already see their variance in quality, aspect ratio, even weather conditions in the game, etc. We obtained these images by extracting the frames from the videos from YouTube, which are freely accessible. And as our goal was to get as much valid data as possible, we focused on the playlist of the football matches, where there were hundreds of such matches. This dataset was later used for the training of the feature extractor using self-supervised methods. We chose SimCLR as the reference self-supervised method. It is a contrastive method where the features from the positive pairs should be as similar as possible, and the features from the negative pairs should be as different as possible. The positive pair consists of two augmented crops from the same image, and the negative pair consists of two augmented crops from different images. We trained feature extractor using the SimCLR method on the if dataset, and we later compared it to our method. We created a new pretext task for self-supervised learning based on spatial understanding of the image content. The goal of the task is to predict the relative distance of two equally sized crops from the same image. The original image is first rotated by a random angle from the interval of -10 to 10 degrees, and then a random crop is performed. The same procedure is repeated also for the second crop, while the angle of the rotation is random each time, and thus it may differ from the first angle. With this rotation, we attack the sensitivity of convolutional network to the rotation of input image, when even a slightly rotation can cause the outputs to be diametrically different. Additionally, we force the network to see similarly to human, who can understand even a slightly rotated image. The distance of the crops is relative to their size, so if a crop has a size of 100 by 100 pixels, then two crops whose centers would be 100 pixels apart would have a relative distance of 1. Determining the relative distance is not always equally challenging, and if the crops overlap, it is much easier to determine their exact distance based on the common points. On the other hand, if the crops come from the opposite parts of the image, it is much harder to determine their exact distance. Therefore, we modified the loss function, which now considers the distance of the crops, based on the formula on this slide. The nature of the task results in 3 possible scenarios of the mutual position of the crops. If the crops overlap, it is easier to determine their distance, and therefore, in this case, the error of the neural network will be more penalized. We consider the case when the crops are diagonally next to each other as reasonably demanding, and therefore, in this case, the coefficient will be equal to 1, and the resulting loss will not change. In the case when the crops are far from each other, it is much harder to determine their distance, and therefore, in this case, the possible error of the network will be less penalized. The coefficient alpha and beta determine the function for the coefficient. Their default values are set just so that in the middle case, the coefficient will be equal to 1. We used action spotting challenge from SoccerNet to evaluate the performance of the feature extractor models and the self-supervised learning methods. The goal of this challenge is to identify 17 football actions which are shown in the graph, like as a goal when the ball goes out of play, direct free kick, etc. The graph also shows the percentage representation of the actions in the dataset. The SoccerNet dataset contains records from 550 matches from the professional European leagues, plus the UEFA Champions League, and relevant annotations to them. In the collage on the right, we can see a sample of some images from the dataset. This slide shows the training pipeline for the action spotting. First, the features are extracted from the whole dataset. The extraction of the features is a separate process which happens before the training of the classification head. This allowed us to replace the default feature extractor with our feature extractors trained either with the SimCLR or our method. The setting of the classification head did not change, and it was trained from scratch each time after swapping the features. This way we could say that better results were achieved thanks to the use of a better feature extractor and vice versa. The classification head has to predict the exact time occurrence of a certain action in the video. Subsequently, it is evaluated for different time intervals delta, whether the action was hit or not, which is represented by the number of true positives, false positives, and false negatives. Based on this, the average precision is calculated for individual deltas, and next, the area under the curve is calculated, which represents the average precision for one class. After repeating for all classes, we get the mean average precision, which is the main metric used in the SoccerNet action spotting challenge. Based on the training of feature extractors, we managed to achieve the result shown in this table. The best results from several trained models, and also for both methods and both datasets, are shown with the if 000-002 representing a subset of the entire if dataset. The first row represents a results that were achieved using the features provided from the SoccerNet, and they were extracted using the pre-trained ResNet 152 model. In other results, a smaller model was used due to the available capacity, and we chose the EfficientNet P0. It can be seen from the table that the best results were achieved using the pre-trained models. The feature extractor trained with the SimCLR method achieved worse results by roughly 3%, and the feature extractor trained with our method lags behind by less than 5%. What is interesting is that the feature extractor trained on the subset of the dataset achieved better results than the feature extractor trained on the entire dataset in the case of the SimCLR. We repeated the trainings also on the ResNet 18 model while maintaining the structure of the evaluations. Again, the best achieved results from several trained models are shown, and again, the pre-trained models achieved the best results. However, the feature extractor trained with our method outperformed the feature extractor trained with the SimCLR method on the if dataset and achieved only 2% worse results than the best ResNet 18 model trained with the SimCLR method. This shows the potential of our method and proves its appropriateness and correctness. And with this great success, I have come to the end of my presentation. Thank you for your attention, and I will be happy to answer your questions.
Okay, thank you very much for this great success. And now it's time for your questions.
Thank you for the presentation. So I have a question. This pretext test of yours seems somewhat ill-posed, because if I have like people in the middle of the field where there are no markings, right, then it would be even difficult for a human to tell me exactly where they are, because they could be moving within it. So my question is, during the training of this pretext task, did it actually obtain like good accuracy in terms of predicting the actual distance? Because it would seem to me that this is quite difficult to do even for a human, and I don't know if the network has the capacity. In some cases it does, because maybe you see some line markings and so on, and when they are close, that you showed that it is. But this seems quite difficult as a pretext task. So, what was the performance on the pretext task in terms of like the accuracy of the distance that you predict?
Yes, thank you for your question. As you mentioned, yes, it is quite difficult even for humans. That's why we introduced the customized loss when we less penalize the network when the crops are far from each other. And in the case of accuracy, I believe that the mean absolute error was about 0.3 in the trained models. But it is not our main goal to. Obviously, we want the pretext task to work so that the neural network is learning and the loss is less. But the main goal is that the feature extractor will be performing good on the downstream football task. So even if the pretext task is demanding and maybe it is hard, but if it can serve as an tool to learn something and then use it in the downstream task, for me it is quite good.
Have you considered like doing some combination of maybe your pretext task for some of the maybe simpler cases and the SimCLR, or maybe even just not using the difficult ones? Just using have you tried some variations of this? Because maybe just concentrating on the easy samples would also create a good feature detector, right? Maybe using the ones that are too difficult even for humans, maybe those are not that beneficial.
Yes, we haven't think of combining the pretext task. We focused, we wanted to create our own from scratch, and by combining it. It would be interesting to see the results, whether it will help in the hard scenarios when the crops are far from each other. And thanks for the thought.
Thanks for the answer.
Okay, is there any other question? Okay, if not, I have one short question. So what was the distribution of the training samples in these different classes? Were there any classes which were really underrepresented? And if yes, how would the MAP works for this? So if there are some classes which are represented just by very few actions in these videos, so would it mess the MAP up, and how the network learned for these classes?
You mean the action spotting challenge?
Yeah.
Yes. We can see the percentage representation, and also we can see that the actions are divided into shown and unshown. We can see that, for example, the goal, penalty, red card, and the yellow to red card, that are all only shown actions, and that is that they were visible on the video. Like, for example, if you have some yellow card, it can be that the video didn't capture it. It happened there was focus on some active action that they were attacking, and the referee then went back and give the yellow card, but it wasn't shown on the video. And actually, the action spotting is divided into three metrics. The main metric is the average, mean average precision, but there are also separate metrics for the shown actions and unshown actions. And yeah, combining them, we can see whether it performed well only on the shown actions or whether it could capture the unshown actions also.
Thank you very much then for the talk. Thank the speaker again.
Send to the beach where the pixels play, from rendering to VR. It's a pixel